Morning, everyone. We're going to start with just a quick review lesson of Coulombic force and Coulombic attraction repulsion. It's something that we had done before the school closure, but we need to just review it really quickly because it's going to play a key role in all of the periodic trends and properties and stuff that we're going to be working with from now up all the way through reactions. To recap, remember Coulombic force is the force of attraction or repulsion between two charged particles. We can call it Coulombic attractive force if those two charges are opposite, or we call it the Coulombic repulsion or the repulsive force if those two charges are the same. The way this ties into the atoms and chemistry is because we know that in the atom we have charged particles. We have the protons and the electrons, or in the case of compounds, we have cations and anions with also charged particles that would interact with each other as well. The formula for Coulombic force is given down here. The force is proportional to the two charges, the positive and negative charge, or the two positive charges, the two negative charges, and it's inversely proportional to the distance between those two charges. So in the case of Coulombic attraction, in our sense for chemistry, we're talking here about the charge of the nucleus, and we treat the nucleus as one big positive charge because it is so dense. All those protons are essentially right on top of each other. So compared to the electron that they're attracting, we treat them as just one point. For the negative charge, we're talking about an individual electron because we know that those electrons are spread out all around the nucleus itself. So it's not that all of those electrons are built up. Their charge is not one giant negative charge. We treat them individually. And then on the bottom, we have R, or D, right? The distance or the radius between the nucleus and those electrons themselves. And from this relationship, we know that as either the two Q's get larger, force would also increase, or as the distance between those two charges increases, the force would get smaller. If we're talking about the repulsive force, then instead of talking about the nucleus to the electrons, we'd be talking about the protons with the other protons, or we can talk about the electrons with the other electrons and the distance between those. For most of the work with the trends, we're going to be talking about the nucleus to the electrons themselves. And the one graph we had already kind of looked at together as a class was this one here with ionization energy versus atomic radius. We use this to support the relationship between distance and force from the Coulombic attraction law. And the reason we did this was we were looking at what would happen to ionization energy as the force of attraction increased and decreased. And we know that if the attractive force is really, really high, then the amount of energy needed to remove that electron and to separate it from the nucleus would also be really, really high. So here on the left side of the graph where we have a really high ionization energy, this must mean that the force of attraction is also really high for these atoms. Whereas over here on the right, where we have a low ionization energy, the force is going to have to be really low. Since our equation is that force is proportional to the two charges over the distance squared, it makes sense then that as the atomic radius increases, it's going to have a decreasing effect on the force, and if the force goes down, the ionization energy should also go down. We also see that here R is squared, meaning that this relationship is not going to be linear. We see instead that it is a curve. So initially, small changes in the atomic radius have a really, really big effect on ionization energy, but once those radii start to get larger, the effect they have on the ionization energy starts to diminish, right? Because we're already dividing by a really large number up here in the formula. So it's going from dividing by a really large number, like let's say 100, to dividing by 101 squared, where it's not going to affect the force as much as going from, say, 1 to 2, even though there's just a 1-point difference in both cases. We're going to take a look at each of the different trends individually and kind of examine how the atomic structure plays into them, and then how that leads to different patterns in the periodic table we can use to our advantage when predicting reactions, bonds, equations, models, and molecules.